Talk to me about how I would calculate how much I pay. What do you guys think? If you knew how much electricity you used, how would you calculate the cost? What do you think, Lily? So guys, try to think of just like just in the real world. Forget about algebra for a second, about functions. Just like if you were given this information on your bill, and you knew how much electricity you used, would you be able to figure out how much your bill is going to be? How would you do that? Madison, what do you think?
Just add, like, or I don't know, see how much input there is. So, 10 cents for the first 200, and then
Okay, so let's say we used 100. How much would that cost?
100 times 10 cents.
So we do the amount of electricity we used times 0.1, yeah? Will that always work? When will that work? Up to 200. So if I use less than or equal to 200 kilowatt hours, then all I have to do is multiply that number by x, or sorry, by 0.1. And I made it greater than or equal to 0, right? Because we can't use a negative amount. And I mean, we could argue about the greater than or equal to there, like strictly greater than 0 might make sense, because if you don't use any electricity, are you really going to care how much it costs? But so if you were to have a greater than there for greater than 0, that would be fine too. We're presuming that we have electrical service, so theoretically we could use no electricity, I suppose. But what happens after that, like if you use more than 200, then this kind of falls apart, right? We can't just multiply by 10 cents. So then what would you have to do? So 15 or 0.15, so that's 15 cents, right? Times what? Times x? So if you use 300 kilowatt hours, I'm going to use 400 actually because it's a nicer number. If you use 400 kilowatt hours, would it cost you $60? It wouldn't? Because that's what 300 times 0.15 is, I hope.
Is that
Yes.
X 200?
Okay, so plus, do you mean like this?
Yeah.
Very close. Do I want to pay for 200 more kilowatt hours?
Less?
Yeah. Like we don't want to pay twice for that 200, right? So we only pay 15 cents for the number of kilowatt hours over 200. So like if I used 400 kilowatt hours, then I would multiply 200 by 0.15 because I don't want to pay for that first 200 again, right? But I have to pay for it once. So is this my total cost? Just if we're just looking at the bottom line. Did I pay for all of my electricity? Like if I used 400 kilowatt hours and I took 0.15 and I multiplied it by 400 minus 200, did I pay everything I need to pay? What else do I have to pay? Yeah, I have to pay for the first 200, right? Which is 10 cents times, well, we can just say times 200 because we know that we used that first 200, right?
Why do minus 200?
So because I only want to pay 15 cents for the number of kilowatt hours over 200 that I used. So like if I use 300 kilowatt hours, I wouldn't pay 15 cents times 300. I would pay 15 cents times 100 because I used 100 more than the initial 200 that I already paid for. So think about it this way. If you use 300 kilowatt hours, how many kilowatt hours do you have to pay 15 cents for? Just 100, right? So that would be 300 minus 200 is how we get that 100. So we're taking off what we already paid for. Good. But again, this model falls apart too. Like, it doesn't always work. In fact, like if I used 100 kilowatt hours, would this give me $10? Because we know that's how much 100 kilowatt hours would cost, right? 10 cents each. If you plug 100 in there, do you get $10? We don't, right? Because we get the negative 100 that we multiply by 0.15, which is like saying that they're giving us back 15 cents for everything less than 200, which they're not going to do. So this is only valid if x is greater than 200, right? So we have two perfectly good models that will give us accurate answers, but neither of them will always give us an accurate answer. One of them will give us an accurate answer up to 200 kilowatt hours, and the other one will give us an accurate answer after 200 kilowatt hours. So this is what we call a piecewise defined function. It's a function, it's a single function. It relates a single input and a single output and describes a single situation or relationship. But the rule that you use to calculate your output is different based on what your input is. So if our input's less than 200, we use the rule multiply by 0.1. If our input is greater than 200, we use the rule subtract 200, multiply by 0.15, and then add 20, which is what 0.1 times 200 is. So the way that we write this as a single function is we use a curly bracket, just one. It doesn't get like closed on the other side. It's just kind of as a brace, like grouping those together. And then we say e of x is equal to. And so that's read like e of x is equal to 0.1x if x is between 0 and 200. E of x is equal to 0.15 times x minus 200 plus 0.1 times 200 if, I didn't write my if, x is more than 200. So on the right side, it tells you how to figure out which rule to use. So if I want to evaluate e of 150, what's my x value? My x value is 150. And so to evaluate this, the first thing I do is I look over here and I say, okay, is 150 between 0 and 200, or is it greater than 200? Yeah, it's between 0 and 200. So 150 is between 0 and 200. I'm not going to have enough room if I leave that there. So 150 is between 0 and 200. So I'm going to use the first rule. E of 150 equals 0.1 times 150, which gives me 15. There would never be any occasion whatsoever, well, for this relationship, that I would plug 150 into here, because that part of the function doesn't even exist for an x value of 150, right? It's not like we plug it into both. It's always one or the other, and it's just based on what our x value is. So if I wanted to calculate e of 200, is my x value between 0 and 200, or is it over 200? It's between. So 200 is between 0 and 200. So I'm going to use the first rule. So E of 200 is equal to 0.1 times 200, which is 20. And then what about to evaluate E of 300? It's greater than 200, right? So that tells me to use that second formula. So 300 is greater than 200. So use the second rule. So E of 300 equals 0.15 times 300 minus 200 plus 20, which is 35. So that's how we evaluate piecewise defined functions, is if we're given the function and we want to evaluate f of 10 or whatever, we look first at the right side and figure out which one of the regions it falls in, and then use the corresponding formula. Again, you will never plug a number into both pieces of a piecewise function. The first thing you do is choose which piece you're going to use, just like we did here. For the first two, we said, okay, I have to use the first rule, and for the last one, we had to use the second one. So we're just plugging into part of the function because each formula only applies to some x values. Does that make sense? So far, so good? Okay, so we're going to just sketch a really rough graph of this function, and then we'll get into more specific graphing for these guys. So my x value is the number of kilowatt hours. And my y value is the cost. And what we want to think about is like, okay, I know how to graph y equals 0.1x. You guys know how to graph that too, right? You could make a table of values, or you could say, oh, that's linear because there's no exponent or square root or anything, and so it's got a slope of 0.1, a y-intercept at 0, 0. You could graph it that way. But regardless of what type of function it is, if we have an equation like that, we always can graph it, right, just by picking x values and plugging them in and figuring out what y is. So we want to graph y equals 0.1x, but we only want to graph it for x values that are less than 200. So we have 200 right here. And I know that when x is equal to 200, my output is 20, because we figured that out right in the middle there. And so I have a point here at 220. And I also know that if I don't use any electricity, it's not going to cost me any money, right? 0.1 times 0 is 0. So there's a point down here at 0, 0. And I see that this is a linear function. Hopefully you guys recognize that as well. If not, again, when all else fails, just plug in numbers for x until you get the shape of your graph. But this one is linear, so we can just draw a straight line, like so. So that's the first piece. And then the second piece is going to look exactly like the graph of y equals 0.15 times x minus 200 plus 20, which you could simplify, like we could distribute and all that stuff. But what I notice about it is that it's also linear. Yeah? You guys see that too? And that its slope is 0.15. And so it's going to be steeper than the first part of my graph. So like I said, we're just doing a rough sketch here. So I'm just going to make this piece a little bit steeper. So I graphed two separate lines. But instead of graphing them like I normally would, where I extend them both as far as I can and put arrows on the end, one of them I only graph between x values of 0 and 200, and the other one I graphed for all the x values to the right of 200. So this part of my graph is the graph of y equals 0.1x, and this part of my graph is the graph of y equals 0.15 x minus 200 plus 20. And again, we weren't super exact with that, but we're going to get into the details of graphing these more perfectly. We just wanted a general sketch. The important thing to notice is this. The first thing I found was what we call an endpoint right here. That's where we switch from using one equation to the other. That's what's going to tell me where to stop each line or curve. Any questions so far just on our general sketch? That makes sense what we did there? Okay, so let's talk about how to graph more specific graphs of these piecewise functions. We have just sort of a standard procedure that lists for us the things we need to think about. So the first thing we want to think about is where the boundaries are. So we're going to find our boundaries first. And in general, your boundaries are going to be at those places where, like in the inequalities, where you switch from using one to the other. So in this case, our boundaries were at 0 and at 200. So because we graphed one graph between 0 and 200, we graphed one equation, and then we graphed another equation to the right of 200. So those boundaries just tell me when I'm switching from one equation to the other, so I know when to stop my line. The second thing we want to do is find endpoints. And determine if they are open points or closed points. So in this case, our endpoints were at 0, 0 and at 220. So when I graphed, the first thing I did was I found this point that was on that boundary line, and then I found this point that was on that boundary line. And both of them I use closed points for because the symbol between the 0 and the x, for that formula, the symbol between the 0 and the x was or equal to, so I fill in that point. The symbol between the 0 or the x and the 200 was also or equal to, so I filled in that point. Now, when I graph that second piece, theoretically, this endpoint would be open. The reason that we don't end up seeing that in this graph is because they meet up. They don't always meet up like that. In application problems like this, they often do, because I'd be pretty mad at my electrical company if up to 200 I paid a certain thing and then it just like jumped right at 200.0001. It like jumped $50, right? That wouldn't make a lot of sense. So often these end up being continuous without any gaps just because of that fact. But if they hadn't met up, I would have an open point on the graph on the right. And we'll see one of those here in a sec. So far, so good? So then the last thing we're going to do is we're just going to use a table to find additional points to complete our graph. So that part of it is really just going to depend on how much you remember about general shapes of graphs. If you find your parent function notes from earlier in the semester, we talked about the general shape of like the squaring graph and the cubing graph and the square root graph and all that stuff. So if you know the general shape, then you're not going to need as many points in between your endpoints to figure out what the graph is going to look like. So if you can find those notes and try to use them as far as like not having to graph every single point on the graph, then that can be really helpful. But again, when in doubt, just plug in your x values and make your points, and you'll be able to see it. Okay, let's do one of these. So you don't have to do this like on tests and stuff, but since what we're used to doing with inequalities is graphing them on a number line, I'm just going to show you what that looks like on a number line, and then we're going to transfer it down to our graph. So on a number line, if I were to graph these two inequalities, I would have like 2 here and 6 here. And I'd say, okay, I'm including 2. And everything to the left of 2, that's this guy. And then between 2 and 6 is not including 2 here, is including 6 here. So it's everything in here. So the idea is we're given these 2 regions, and we're told to use one equation for the green area and the other equation for the red area. So the first thing I want to do is put, right, like this says use this equation for all the x values in here, and use this equation for all the x values in here, is what my piecewise function tells me to do, right? If we were evaluating this and I gave you, if I wanted like f of 0, we would say 0 is less than or equal to 2, so I'm going to plug it into -1/2 x minus 1, just like we did with our previous function. So the first thing I'm going to do is just draw my boundaries. So the boundaries happen when we make a switch from one to the other, or when we stop the graph. So here and here, I either switch from one rule to the other one, or my graph stops. So we are going to put, I just use dotted vertical lines at 2 and then at 6. And my function is saying if x is less than or equal to 2, so that's everything to the left of 2, I want to graph y equals -1/2 x minus 1. That's the equation that I'm going to graph in that part of my graph. And then if x is between 2 and 6, well, if x is between 2 and 6, I use the square root of x minus 2. Try not to overcomplicate this, because you guys know how to graph functions. Like, you know how to graph equations, right? You just make a table, you plot some points. The only change here is that we are stopping our graph at a certain place and then doing another graph at a certain place. So we're just breaking separate graphs up into smaller pieces. So I think the easiest way to do this is to just make a big table. So I usually do 3 columns. You're going to list your x values in the first column, your first rule in the second column, and your second rule in the third column. And if there happen to be more rules, it doesn't just have to be 2 rules. It could be 3 or 4. You just make a column for each one. So let's list some x values. You want to start well to the left of your first boundary. Definitely include some negatives in there. So I'll start at like -2. 1, 2, 3, 4, 5, 6. I generally don't skip x values when I do this, because I don't want to accidentally skip over a boundary or something like that, or not be quite sure where to stop. So we said the next thing, so after we find our boundaries, the next thing we're going to do is find our endpoints. So the endpoints, those are just the points at the end of each section of your graph. And they happen at those boundaries. So at 2 and at 6. So let's start with x equals negative 2. Well, which formula should I use there? The one on the left or the one on the right? So if x is negative 2, it is less than 2, right? And so I should use this equation. Yeah? So here, let me get rid of all that writing to not overcomplicate. So remember what we did when we were calculating the cost of our electricity. I look at my x value. I say, okay, my x value is negative 2. Is it less than or equal to 2, or is it between 2 and 6? Yeah, the number negative 2 is less than or equal to 2, and so I'm using this formula. And in fact, I'm going to use that formula all the way until I get to 2, right? For all the x values less than 2. So I'm just going to go like this. So now I don't even have to, until I get to that yellow line, I don't have to worry about which one I'm using. So let's see, we get 1, 0, negative 0.5, negative 1, no, yep, negative 1.5, and when I plug 2 in, I get negative 2. Is that going to be an open point or a closed point? So you want to look on the line that has that rule and ask yourself what inequality symbol is between the x and the 2. Am I including 2 or not including 2? We're including 2, right? So looking at the line with that equation, between the x and the 2, I have a less than or equal, which means that's a closed point. So we have a closed point at 2, negative 2. And then this is a linear function, right? So I really just need one more of those points, but by all means you could plot them all. And then we'll draw a line. Make my colors match here. Okay, so that's the first piece. And like I said, we graph that exactly like we would normally graph y equals negative 1/2 x minus 1. The only difference is that we stopped when we got to 2. So now, those endpoints you always want to plug into both of the equations, because even though we're not including 2 on the other end, or on the right side, we want to get infinitely close to it. So the way that we do that on a graph is using an open point, right? So I'm going to plug 2 into my second equation. 2 minus 2 is 0. The square root of 0 is 0. Whoops. And what kind of point is that going to be? It's going to be open, right? If we look at our second line, because that's the column we're in now, we're using that formula, and we look between the 2 and the x, it's a strict inequality, which means we're not including that point. So it's going to be open. But then I know between 2 and 6, I'm using that second formula, right? So I'm just going to put, again, like an x here, so I don't accidentally plug things into the wrong thing. And then we're going to go down our list and start plugging x values into our square root function. So 3 minus 2 is 1. The square root of 1 is 1. 4 minus 2 is 2. This is the square root of 2. Square root of 3. And then 6 minus 2 is 4. And the square root of 4 is 2. And I'm at another endpoint, so I have to ask myself, is that point going to be open or closed? It's going to be closed. Good, because if we look at the line that contains the formula we're using, In between x and 6, there's a less than or equal, which means I'm including that point. So this is closed. And so this is where, like, if you know the general shape of these parent functions, it's a square root function. So if you know the general shape of it, you can just do, let's see, 2, 0 is right here. That's our open point. And then 6, 2 is our close point. And if you know the general shape of the function, then that's enough. If not, you should plug square root of 2 and square root of 3 in your calculator and get some decimal approximations. But it looks basically like that. I don't know if it's annoying that there's things in here, but there we go. Any questions about that process? So the way I kind of think of it is just like graphing two equations, right? We made a little table for the first equation, then we made a little table for the second equation. And so just like we normally do, we're just not extending the lines. We're stopping at those boundaries. You guys want to do another one? Okay, so again, we're going to start with the boundaries. Now, the first thing I notice about this is that if I read my function, it looks a little bit different because in the middle there I have one of my regions. It just says x equals 2. So it's just giving me one x value. So right here, that didn't do a very good job. Right here. What that's saying is at the point where x is equal to -2, y is equal to 0. So anytime you have an equal sign there, they're just giving you a single point, like one ordered pair. So this is the point -2, 0. And you can plot that point, and then you're completely done with that line. Like, that was the easiest part. We just get to throw it out. So -2, 0 is right here. And then this guy is done. And now we'll work with the other two pieces. So I have a boundary at -5. And really for these boundaries, if you're getting mixed up at all, just look at the numbers that are in the inequalities. Like literally, it's just those numbers. So on the last one, we used 2 and 6, right? Those are the numbers we see in the inequalities up there. On this one, we're going to use -5 and -2. So I have a boundary at -5, and I have a boundary at -2. And let's see, to the left of -5, my function doesn't exist, right? It's not defined for x values that are less than -5. Between -5 and -2, which rule am I using, top or bottom? What's the output of that one? It's 2, right? That's a constant function. It's saying that y is equal to 2 no matter what, well, not no matter what x is, but if x is between -5 and 2, and -2, my y value is just 2. So this is going to be the line y equals 2. Remember, that's like a horizontal line. And then if my x value is bigger than -2, notice that this means the same thing as, not that, as this. With piecewise functions, it's often written in this order, the order they gave you here. Just so, I don't know, I guess they like all the inequalities to face the same direction for consistency. But that just means that x is greater than -2. So to the right of -2, we're using y equals the absolute value of x minus 1. So let's make a table. And we've got x, and then y equals 2, and y equals the absolute value of x minus 1. So I'll start at -5 because nothing exists to the left of that. So -5, -4, -3, -2, -1, 0, 1, 2, 3. That should be enough. If you find that you don't have enough points, then you just add to your list. But we'll talk a minute about how to tell if you have enough points or not when we get to the one that's not linear. So my boundaries, again, are at -5 and -2. At -5, which rule am I using, the top one or the bottom one? The top one. And we're going to use that all the way up to -2, so I'll just make my x here so I don't forget. And when x is -5, what's y? 2, right? It's a constant function, so no matter what x is, y is 2. Is that point going to be open or closed? It's going to be closed because if I look at this first line in between the x and the -5 is a less than or equal to, which means I'm including that point. If you're not sure where to look to figure that out, if you're in this column, then you're in this row, right? So whatever that equation is in the column we're using, that's the row we're going to look at to figure out if the point's included or not. So this is closed. And then no matter what x is, y is 2. So 2, 2. And now we've hit our next boundary. Is that point going to be open or closed? It's going to be open. So I'm in the column that says y equals 2. Here's the row for y equals 2. And between the x and the -2 is a strict inequality. Yes?
Why did we include on the first equation?
You mean where x is -5?
Yeah, we just put open? Because it's technically not including the 2 on the first equation.
So it's not 2.
-2.
It's, do you mean this one
Mm-hmm.
or this one?
I mean, -2 for the first equation.
Yeah. So we just said that was open
Oh.
because of this inequality right here. Good. So now I'm ready to draw that line. Oops. And again, it's just a horizontal line. So we said -5, 2 is closed, and -2, 2 is open. And then I have a horizontal line in between. And now we'll switch over to our next equation. If I plug -2 in, I have the absolute value of -2, which is +2. -1 is 1. And is that going to be included or not included? Open or closed? Also open, right? If I look on the line with that equation, and I look between the -2 and the x, it's a strict inequality, so that's also open. And then all the x values bigger than -2, I'm only using that absolute value function. And so I can put an x here, don't have to worry about it. Absolute value of -1 is 1, -1 is 0. And then what's the general shape of the absolute value function? It's like a V. So because we know that it's going to be a V, you want to keep plugging in x values until it actually turns around, right? Like, so that's one way to figure out if you've got enough points, is if we just plotted like 3 points and it looked like a line, then that wouldn't give us an accurate graph. So because we know it's going to be a V, we know it has to start getting bigger at some point. So 0 - 1 is -1, 1 - minus 1 is 0. Oh, there, now it turned around. So now I know that I've got like the bottom of my V in there accounted for. And you could keep going here if you wanted to, but. So we have an open point at 2, 1. That's very large. And then negative 1, 0, 0, negative 1, 1, 0, 2, 1, and 3, 2. So they're straight lines because it's an absolute value, but we've got to get that V in there. So there's my graph. Just take these step by step, just like we did together. Really, like, ask yourself all those questions. Because like I said, this isn't something like, it's really easy to overcomplicate these, but like, all we're doing is making tables and plotting points. The end points where you have to figure out if they're open or closed, those are probably the trickiest part because that's the new stuff. But just like we did, just go through step by step and ask yourself all the questions that we asked ourselves, and you'll get it. Don't try to look at it and figure out what the graph looks like, because you probably won't figure it out all at once. But if you go step by step like we did, it should be manageable. We have a couple minutes. Let's just talk real quick about domain and range. What's the domain of this function? Uh-huh. So negative 5, which we're including because we have a closed point there, and then all the way up to infinity. Because even though my graph has more than one like separate piece, so it's not continuous, there aren't any horizontal gaps, right? We don't actually skip any x values. We go from negative 5 up infinitely close to negative 2. Then we have that one single point at negative 2. And then we start up infinitely close to negative 2 again. So even though it's in pieces, we're not actually skipping any x values. What about my range? Yep, it's negative 1 to infinity. And again, there aren't actually any gaps because, like, for instance, right here, it sort of looks like there's a gap between those 2 points. But if we come over here, those y values are accounted for on that part of the graph. So every y value from negative 1 all the way up to infinity is accounted for, in fact, just by this part of the graph. So it doesn't really matter how many gaps are happening on the other side of the graph. As long as there's a point on the graph with the y value, it's part of the range. So try not to be daunted by like all the different pieces. Just look overall at smallest and largest, and then follow it and see if there are any gaps. Because sometimes there will be a gap, but you can see it. If you draw, if you shade in a region where you think there's a gap, if there is no part of the graph that is in that region, then there's actually a gap in your y values. Make sense? Okay, so you have 3 things to do tonight.